All right, welcome back to Codex. Emily King is an assistant professor at Colorado State University. Professor King got her PhD from the University of Maryland under the direction of John Benedetto. After graduate school, she did postdocs at NIH, Osnabrück, Bonn, Berlin, before landing a position in Bremen. After 5 years in Bremen, we finally lured her back to the States with promises of Rocky Mountain vistas, craft beer, and fourth wave coffee shops. Emily is an accomplished marathon runner, but her endless supply of energy also comes in the form of an infectious enthusiasm for mathematics. She has a broad research program covering topics from frames to codes to p-adics to shearlets to neural nets. In addition, Emily has a penchant for organizing influential workshops around the world, and the literature contains several papers that credit these gatherings as their source of inspiration. In fact, today's talk is based on research that began at such a workshop last summer and was inspired by another talk in this very seminar. So we're very pleased to have my fellow Codex organizer, Emily King, tell us about a potpourri of Projective T Designs.
Thank you very much, John, for that nice introduction. It actually was a nice introduction. Far too often people say that, but that was quite nice. And just as a little point of clarification, Wojtek Chaya was also one of my advisors. I don't want to leave him out. But speaking of my advisor, John Benedetto, he was obviously influential in my research, but he was influential in the choice of this title. So potpourri, if you've read any of John's writing, you see this word potpourri very, very frequently. But potpourri is also something where you think of, you're just mixing a bunch of things together and putting some fragrance on and hoping it all turns out. So that's kind of what this talk is. Due to a mix-up that was not our fault, but my fault, Elena Robeva was supposed to be speaking today, but I forgot to tell her that. So I had to step up. But it ended up being a little serendipitous because just last week, two of my Codex co-organizers, Joey Iverson and Dustin Mixon, and I posted a paper to the archive, and it really ties in a lot of the themes that we've seen here in Codex, including, as John mentioned, a section that is inspired directly from a Codex talk. So hopefully my fragrance of mixing all these jumble of things together will actually be pleasant in a potpourri of Projective T Designs. Okay, so for those of you who have seen me give a talk in frame theory over the last couple of years, you have definitely seen me talk about my favorite set of 9 vectors in 3-dimensional complex space. I'm putting a little caveat here. This is slightly different than the set I'm usually talking about, but and so it actually loses some of the super special properties, but it will make things just cleaner when I sort of generalize this construction in the future. So it's just a matrix that has a 3x9 matrix that has as entries 1/√2 times 1, 0, zeta or zeta squared, where zeta is a primitive third root of unity. And so some of the things that we'll see today is why this particular set of 9 vectors in 3-dimensional space is so special. Okay, so let's go all the way back to basic linear algebra and make sure that everyone's on the same page. And we're really going to dig deep into orthonormal bases and really kind of see what makes orthonormal bases tick. So we'll start off with phi, which is phi j, as an orthonormal basis for FD. So at this point in the talk, when you see a blackboard bold F, it means the reals or the complexes. But we're going to throw a wrench in that later. But for now, let's just think about reals and complexes. Okay, so what do we know about orthonormal bases? What are some of the nice properties? First of all, each vector is unit length. Well, why is that important? Well, that means that no one vector is weighted more than the other, so they're kind of being treated equally. Furthermore, whenever we have any vector x in d-dimensional space over the reals or complexes, we have this very beautiful change of basis formula. So we know, because it's a basis, that we can write any vector as a linear combination of the phi sub j. But because it's an orthonormal basis, we have a very explicit and beautiful formula for those coefficients, which is just x inner product the particular element of the orthonormal basis. Furthermore, the inner products between the vectors and the orthonormal basis are equal and optimally small in absolute value. So these things are, they're all the inner products of any two vectors is 0, but these are optimally spread apart. And we can think about this as saying that vectors represent different information geometrically. So the question is, how can we generalize these traits? But I want to go back to this change of basis formula because there's a whole lot of information that's packed into that. So let's write out phi this time, and instead of thinking about a list, I'm going to be a little abuse notation and write phi as the matrix that has as its columns phi1 to phi d. Then how can we rewrite this change of basis formula? Let's take an arbitrary vector x and fd. Then the change of basis formula here, that is the sum from j equals 1 to d of the inner product of x vj and vj, that can be rewritten a couple of different ways. So let's move one step to the left. And what are we looking at? Well, the columns of phi are phi1 up to phi j. So if we want to have a linear combination of the columns of phi, where the coefficients are these inner products, that's the same thing as saying we're taking the vector of those inner products and multiplying on the left by the matrix phi that has as its columns of phi sub j. And now we want to write the ability to get this column of inner products in terms of a matrix multiplication. And this vector that's the inner products of x with phi sub j is precisely equal to the matrix product of phi star times x. So phi star, we flip it, and what we end up getting is all the rows are phi j stars. And so all of these entries here of this phi j star x is just going to be the inner product of x with a particular phi j. And we can rewrite this matrix product phi j as this sum of rank 1 outer products here, where that matrix is precisely the sum of phi j star for j equals 1 to n. So why does this work? Why, if we take this little pipeline, so these 4 different sort of equivalent ways of writing this out, why does that equal x? So in general, yes, it's an orthonormal basis, but we didn't actually need the columns of phi to be an orthonormal basis. What we actually needed, if you look, is we needed that the rows of this matrix phi, where the columns are the elements of orthonormal basis, we need that those are orthonormal. Now, of course, when you're talking about an orthonormal basis, if you make the columns of a matrix orthonormal, then the rows have to be, because you're living in the realm of orthogonal and unitary matrices. But we're going to generalize this topic, and what we're going to see is we can stack up other vectors as columns. And what we need for this change of basis is that the rows of this new phi matrix that might not be square anymore is just equal norm and orthogonal. Or in particular, we could say they're orthonormal. And you see right here, what's important is we're writing phi star. If the rows are orthonormal, then that has to be the identity matrix, because that's just giving you the inner products of all the rows. There's another way that we can think about this change of basis formula, and it's to use this little formula that we have on the left, is that the outer products of the columns, so the phi j stars, they yield a decomposition of the identity matrix. So what we're going to do is dive even deeper in what it means for having this matrix phi where the rows of orthonormal, and some special properties that come from that. But keep this outer products thing in the back of your mind, because we're going to do something really horrible with the identity matrix and make it be something that it shouldn't actually be, but it's going to allow us to do further generalization. All right, so what I claim is that if we take a unitary matrix, i.e. a matrix where the columns are orthonormal, then the columns of that matrix yield a cubature rule because the rows are orthonormal. Okay, so what is a cubature rule? It's the kind of thing that you might have seen at some point when you're an undergrad and you're like, oh, this is really cool, but you don't really do much with it. But you might have also forgotten. So let's go over it. So I'm calling this an exact cubature rule that says, let's say you have some function class defined on some domain D. So we're looking at functions from D to some C. This is not Blackboard bold, just some arbitrary C. And you need that all the functions are integrable over this domain with respect to some measure sigma. And this Cubature rule then says you have some finite set of points in your domain D, such that if you take any f in your function class, then taking the average of the pointwise evaluation of that f over your set D, over the set of the DJs, is the same as integrating that function over the entire domain. I say exact because Cubature rules are also used for numerical approximation of integration, but here I really mean you're actually getting the exact integral out. So my claim is we're going to get some type of Cubature rule. We have to fix what kind of function space we mean, but it's going to be coming from the fact that the rows of the matrix are orthonormal. Okay. So let's set our D to be this thing here. And this is the notation that I'm going to be using for the unit sphere and CD. And we'll use it for unit spheres and other spaces as well. And our function space is going to be polynomials, complex polynomials in Z1 up to ZD and Z1 bar up to ZD bar. Actually, we're going to have to refine this a little bit. This is too big of a space, but let's just keep it with this space for now. And sigma is uniform measure on the sphere. And we're going to set our DJ to be the columns here of this matrix. So it's unitary. So each of these columns are unit vectors in CD. And so they do indeed lie in this set D. Okay, so let's start with a simple little monomial. And that monomial just maps all of these coordinates to Z1, Z2 bar. Okay. So let's first average the point evaluations. So if we have evaluate P on the phi J, well, what does that do? It takes for any column, any phi J, it picks out the first element of that column, phi J1, and then the complex conjugate of the second element of that column, phi J2. And then we're summing up over all J. But what is that doing? That's just taking the inner product of the first and the second rows of our matrix phi, which those rows are orthogonal, and so that is going to be 0. And if you could see, if we took any ZJ, ZK bar, where J and K are unequal, we're going to get the same result. Okay, so is the integral going to also be equal to 0? So let's integrate here over the sphere. And so one of the traits that we need of this measure that we're integrating over is that it's invariant under unitaries. So the matrix that is the diagonal matrix with -1 in the upper left corner and 1s for the remainder, that is very clearly a unitary. And so we do a change of parameters based on that. And it doesn't change the sigma, but now we get a negative popping out. So we have the integral of this monomial is equal to the negative itself. So that can only happen if the integral is 0. So 0 equals 0. Okay, so let's try a new monomial. Let's try monomial Z1, Z1 bar. So i.e. we're just looking at the modulus squared of the first complex coordinate. So again, we feed in those values from the columns of phi. And just like we saw before, we're getting an inner product of the rows of phi. And this time, the inner product that we're getting is of a row with itself. And since the rows are orthonormal, we get a 1, but we're averaging, so we get 1 over D. Okay, so let's compute this integral. All right, so if we compute this integral, then we're integrating over the sphere, the unit sphere of Z1 bar. And what we end up getting, I claim, is 1 over D. And the other trait we need to use the uniform measure is that the measure of the entire sphere is equal to 1. So we can write run is equal to the integral over the entire sphere. But we're on the sphere. So that is equal to the integral over Z1 modulus squared plus Z2 modulus squared all the way up to ZD modulus squared. And now, again, we use the fact that this measure is invariant under unitary transformations to conclude that the integral of ZK bar, or integral of ZK modulus squared for any K, has to be equal. So all these different things have to be equal, and 1 divided by d is equal to 1 over d. Okay, so we have a cubature formula. It's kind of a dumb cubature formula, but it's still something that works, at least for these 2 functions. Okay, so I told you that we're going to need to be a little more specific than these polynomials, and this is precisely the space that we need for to generalize this concept of the cubature formulas. So I will write Hom FDTT to be the F, so real or complex, span of the monomials that are in Z1 up to ZD and Z1 bar up to ZD bar, where if you sum up all of the exponentials of the ZD parts of that monomial, that is equal to the sum of all the exponentials of the Z1 or the ZJ bars in that monomial, and both of those sum up to T. So for example, Z1, Z2 bar is in the homogeneous polynomials over FD 1, 1, because we're getting 1 for the Z and Z1, and we're getting 1 power for the Z2 bar. Note that if we're playing this game over the reals, then this is just the space of homogeneous polynomials of degree 2t. So that's a typo. That 2 should be a 2t. So a fact is, if you take any orthonormal bases for d-dimensional real or complex space, then you're going to get cubature rules for this Hom FD11 over the sphere over the particular space. Okay, so let's look at another space that we're going to need. And that is the space of tensors. So first, let's just define the space of FD tensor T to be the span of EJ1 tensor all the way up to EJT, where J1 up to JT are between 1 and D. And these different EJs form a basis for FD. So the space of symmetric tensors of order T, which I'll denote SymT FD, is just, it's not quite the span of these things, but what we have is whenever we have a linear combination of the EJ1s up to EJTs. But the important thing is whenever we have one of these terms appearing, then the coefficient for that term is the same for any permutation of the subscripts of the EJs. So let me just pop down for a second actually to this example to make it clear. So this thing on the last line right here, we have E1 tensor E2 plus E2 tensor E1 plus 4 E3 tensor E3. So the coefficient for E1 tensor E2 is 1. And if we apply permutation on those subscripts, we get, there's only 1 because we don't have a lot of room to move E2 tensor E1, and that also has coefficient 1. So the dimension of this as a vector space over F is D plus T minus 1 choose T. And we'll also need this orthogonal projection from the tensors down to the symmetric tensors, pi dt. So as an example, if we have this tensor, of x is 2e1 tensor e2 plus 4e3 tensor e3, then applying that projection p32 is going to yield the symmetric tensor I just mentioned. So e1 tensor e2 plus e2 tensor e1 plus 4 e3 tensor e3. Okay, so we're going to need these 2 different function spaces.
But the missing 2 is a typo?
What missing 2?
Your x is defined as 2 times e1 tensor e2.
Uh-huh.
And the 2 should show up for the projection still.
It splits. So the 2e1 tensor e2 becomes e1 tensor e2 plus e2 tensor e1.
It's orthogonal projection.
Okay.
I think there is actually a little typo that in the displayed thing, the SD, pi and SD should be pi and ST instead.
Pi in, sorry, where?
In the big set in the middle, where it says for all pi and SD, I think that should be all pi and ST.
Yes, you're right.
Okay.
I am surprised it took this long. these slides, I'm getting in by the like skin of my teeth here. So the fact that it took that right now there's like only 2 minor typos that have been found in like this plethora of like brand new slides. I'm pretty proud of myself, but thank you, Joey. I'll fix that. So remember I said I was going to do something really horrible with the identity matrix? Well, here it is. So we can think of the identity matrix mapping d-dimensional spacer real complexes to itself as being pi d1, because the symmetric tensors of order 1 we can just think of as just being vectors. Okay, so let's define type frames, which pretty much everyone in the audience already knows, but I'm going to kind of spin the definition a little bit to suit my needs. So again, we're taking our phi to be this matrix that has columns Vj, but now we're allowing the matrix to be short fat, meaning we're allowing the matrix to have more columns than it has rows. Then we define phi to be a type frame if any one of the following equivalent statements holds. First, we have some positive a such that for all x in our vector space, x is equal to 1 over a times the sum of x inner product Vj times Vj. And hey, up to that a, whether or not that's equal to 1, I mean, that's precisely what we had in our orthonormal basis. So it ends up that we can actually get this sort of a decomposition even when we don't have an orthonormal basis. Also, equivalently, we could say that the rows of phi are equal norm and orthogonal, which, wait a second, that Cubature rule really was relying on the fact that things were orthogonal. And we also used that they were equal norm, but it ends up once we normalize things properly, all that's really important is that it's equal norm and orthogonal, not unit norm. Equivalently, we could say that these set of vectors Vj for j from 1 to n yields a Cubature rule for Ham FD11 over the unit sphere. And this is actually kind of cool. This works even if the Vj don't lie in the unit sphere. It's just due to the fact that we're dealing with homogeneous polynomials. And also, we can equivalently say that there's some positive a, which is necessarily the same as this a that we saw in the first bullet point, such that if we sum up the outer products of the Vj's, then we end up getting a times this, well, it's the identity, but we've now rewritten the identity as be this silly projection onto symmetric space pi 1d. And finally, there's this thing that holds that we didn't really discuss with orthonormal bases, but if we take all of the inner products of all the vectors, and we take the absolute value and we square it and we sum those up, then that is equal to 1 over d times the sum of the squares of the norms of the vectors, and then square that sum. So the a here, when it pops up, is called a frame bound. And anything that satisfies these equivalent statements, we call a weighted projective T design. So this last bullet point is also known as something that saturates frame potential. Okay, so what are some type frame examples? We have these blue vectors here that kind of look like an off-kilter orthonormal basis with a little extra piece added on. We have this purple set of vectors that's just 2 orthonormal bases glued together in a nice way. We have the classic Mercedes-Benz frame, but I always draw it rotated. So we have vectors pointing to like cubic roots of unity. Oh, and then here's that set of 9 vectors in 3-dimensional space. We're finally seeing it for the first time again. All of these things are weighted projective 1 designs, and all of the vectors, all the sets of vectors that are equal length, so everything but the blue set, so the ones that are the union of the orthonormal bases or the equally spaced vectors in R2, or this set of 9 vectors in R2, these are all, you could call them just projective 1 designs. So they're also weighted, but the weights kind of correspond to whether or not you're thinking about the vectors as being equal norm. Okay, so what's the T? Like I defined all these different function spaces and there's this parameter T that's going on. So clearly I'm up to something here. So let's just ignore these CT things. We're going to have some constants that come to play. But for now, let's just think about, we've got our short fat matrix. We're looking at the columns. So let's consider the following statements. So One is that those columns, those phi j, they form a cubature rule for hom fd tt over the unit sphere. Two is the outer products of the t tensors, order t tensors of the phi j's, forms a type frame, and there's typo number 2. I need that these tensors, that the tensors form a tight frame for the symmetric space. So if we sum up these outer products, remember what happens with a normal kind of standard type frame over FD, you sum up the outer products, you get the identity, but the identity is just actually a silly projection on the symmetric space. So if we sum up the outer products of the T tensors, we get some constant times projection on to the symmetric order T tensors. And finally, statement 3, if we sum up the inner products of the phi j's, take the modulus, but now instead of just squaring, we raise it to the 2t, then this is equal to some constant times the sum of the norm squared of the vectors, and then that quantity squared. Okay, and the constants that are coming out are dependent upon whether or not we're in the reals or the complexes, and I have them kind of up here. This should be, the constant for the complexes should be very suggestive because it's d, the inverse of d plus 1, d plus t minus 1, choose t, which is precisely the dimension of the symmetric tensors. And so what we see here is this 3 is really saying, yes, we have a tight frame for the symmetric tensors because it saturates this frame potential. Where in general, this for R, this constant that I'm not going to read out the formula, but when t is strictly greater than 1, these two constants are different. And so what that actually shows us is all of these statements are equivalent when t is equal to 1, or the fields or the complexes. But when t is greater than 1 in the fields or the reals, then 1 implies 3. So we have this sort of kind of a variant of something like a frame potential, but there's a different sort of constant, gives us something that's a cubature rule. Those are equivalent, but 2 never holds. So we tensor up these real vectors, and we don't get a type frame for the symmetric tensors. All right, so projective T designs, we call phi a weighted projective T design if 1 or equivalently 3, or in the case the complex is equivalently 2, holds. And further, if the vectors are equal norm, we call phi a projective T design. And yeah, so 2 design was in the title, so this is the T that we're going to be focusing on. In particular, a lot of what we're dealing with are what I call equiangular projective T designs. In the projective T design literature, these things are called tight, but we already have tight for frames, so I'm just not going to use that in this talk, and I will call it equiangular. So let's let phi be, again, this set of vectors, but now let's just think about we're in the unit sphere. Then we call phi equiangular if there's some alpha such that whenever we take the absolute value of the inner product of any 2 different vectors, then we get alpha. So orthonormal bases are an example of something that's equiangular because you take the inner product of any 2 vectors, you get 0, absolute value of 0 is 0. Now, if phi is a projective 2 design, then n is greater than or equal to d squared with equality precisely when phi is equiangular. Conversely, if phi is equiangular, then n is bounded above by d squared with equality precisely when phi is a projective 2 design. And further, if phi is a weighted projective 2 design, then we have n is bounded below by d squared with equality only when, so this isn't just an if and only if, but only when phi is a projective 2 design. And we have a bunch of different names that are floating around, people in the community and people in this audience, that a projective 2 design with number of elements equal to the square of the dimension can be called a maximal equiangular type frame, or a symmetric informationally complete positive operator value measured, which of course people shorten, and it is shortened to SIC. Okay, so let's go back to that set of 9 vectors in 3-dimensional space. That is a projective 2 design. So it's not too hard to actually compute that the inner product, an absolute value of any two different vectors, is 1/2. And it also is a type frame because if you look at the rows, you can see that they're all equal norm and they're orthogonal to each other. And there's also a neat way to generalize to another projective 2 design of 12 vectors in C3 called a maximal set of mutually unbiased bases, or MUBs. If you use the sort of original set of 9 vectors that I normally talk about, but I'm kind of avoiding for this talk. So what are some open problems? One is Zauner's weak conjecture, which is probably the conjecture that we've heard the most over the course of this seminar, that says for all D, there exists a projective 2 design in CD of D squared elements. Some other open problems consider the existence of these maximal mutually unbiased bases. So for any D not a prime power, does there exist a projective 2 design in CD of D times D plus 1 elements consisting of a union of orthonormal bases? So you glue together orthonormal bases and they end up giving you this 2 design. So for any D not a prime power, another open problem is whether or not there exists a weighted projective 2 design in CD, again, from gluing together D plus 1 different orthonormal bases, but now you might weight the orthonormal bases differently. And there's been a lot of work on certain cases of D, but there's a lot of open cases as well. Okay, so potpourri time. There's 3 main results that I'm going to talk about today, time willing, and they're all related somehow to 2 designs. And I'm just throwing them at you, just smattering of the potpourri. So let's get going. Result number 1. This is the result that was inspired by a talk that Vern Paulsen gave. Excellent talk on July 21st, 2020. If you want to check it out, I highly recommend you go to our YouTube channel, like, rate, subscribe, and check out that talk. So the first result is that the smallest weighted projective 2 design for D-dimensional complex space has size equal to a type of rank of a certain quantum channel, giving an alternate formulation of Zauner's weak conjecture. Okay, so I don't want to go too in depth. Again, Vern gave a really excellent talk breaking these things down. I just want to give the basics of what we are kind of playing around with. So if we have a linear map from D by D matrices to M by M matrices, it's called entanglement breaking if it admits what's called an entanglement breaking decomposition, meaning if you feed a matrix A into this channel, then we can write that as the sum from k equals 1 to n of RKA, RK star, where 2 things must hold. There's another typo there. So the rank of each RK is equal to 1. And furthermore, if we sum up the RK stars RKs, we get back the identity. The entanglement breaking rank of such a channel, denoted by EBR, is the smallest in such that there's some set RK with n elements that gives us this entanglement breaking decomposition. We will be concerned with a particular channel called the quantum depolarizing channel that maps D squared vectors to D squared vectors, not vector, D by D matrices to D by D matrices. And this is how it works. You take a matrix, you feed it in, and what you get out is 1 over D plus 1 times, in parentheses, A plus the trace of A times the identity. So this is known to be entanglement breaking. So we know it has some entanglement breaking rank, and the question is, what is it? So the work that Vern had spoke on in his codex talk there's a lot of interesting things in this paper, but some of the kind of the 3 main results are that the entanglement breaking rank of this quantum depolarizing channel is bounded below by D squared, and you get equality if and only if you have one of these SICs in CD, i.e. if and only if you have one of these equiangular complex projective 2 designs. And furthermore, the entanglement breaking rank of the channel is bounded above by D times D plus 1 whenever D is a prime power. And this is due to the existence of maximal mutually unbiased bases. So seeing these 2 things, wait a second, there were 2 different classes of complex projective 2 designs that I had mentioned, only 2. One was these SICs, these maximal ETFs, and the other was these maximal mutually unbiased bases. So it seemed to be very suggestive that like maybe what's really happening here is something involving complex projective T designs. So another thing that they did that we didn't really get involved with, but I think is really neat in that paper, is that they proved that the entanglement breaking rank, it's lower semi-continuous. So if you have channels that are arbitrarily near to this depolarizing channel, if they have the entanglement breaking rank bounded by d squared, then that also implies Zauner's weak conjecture. So kind of giving some more ways to chip away at this conjecture. Oh yeah, so I just asked this question. Wait, yeah, weren't these the sizes of these complex projective T designs, d squared and d times d plus 1? So could there be something deeper going on? And the answer is yes. One of the main results from this paper that went live on arXiv last week is that the smallest weighted projective T design for d-dimensional complex space has size equal to the entanglement breaking rank of that channel ZD. And so if you kind of scour, you can look around. So first of all, notice here we have this weighted here. So that gives us more chance to sort of squeeze down what that entanglement breaking rank is, because there are more weighted projective T designs than there are projective T designs. And in fact, we can see this entire collection here just by sort of scraping papers, in particular this one by Bodman Haas in 2016 and Roy and Scott in 2007. Gives us this long list of upper bounds for the entanglement breaking rank. And I in particular want to point out this one. So even when D is a prime power, there's a way, so you know by mutually unbiased bases that you have this upper bound is d squared plus d, but you can actually squeeze out one from that if you're weighting things in a certain way. Okay, so I said that was going to be quick. That was result one. There's a lot of interesting stuff going on. Also highly recommend that you check out Vern's paper. Result two is that each projective T design over the quaternions is associated with some nice, in quotes, configuration of three-dimensional subspaces of some real Euclidean space. Okay, let's just do a hyper quick quaternion review. The quaternions, H, are four-dimensional real vector space where we can think of it as the span of 1, I, J, and K, where multiplication is associative but not commutative. And we have this property holds that I, J, and K all square to be -1, and I, J, K is also equal to -1. So what that means is you have things like IJ is equal to K, but JI is equal to -K. So it's not commutative. However, there are no zero divisors, and it is associative. So linear algebra over H, for some things, it's just like you're doing linear algebra of the complexes, but sometimes it's a little hairy. So the biggest concern that's just like when you're getting your hands dirty and just doing simple linear algebra is really keeping track of scalar multiplication, because right multiplication is not linear. So how you do that scalar multiplication is important. Okay, revisit. What's the T? All right, now we're going to let F be reals, complexes, or quaternions. And now we're going to make this little parameter M, and M is the real dimension of our division algebra divided by 2. So M is equal to 1/2 when we're over the reals, it's equal to 1 over the complexes, and it's equal to 2 over the quaternions. And then we're going to define this constant here. I wouldn't be too worried about that. Just know that in the case that F is the reals or complexes, it's exactly the constant that we saw on that previous slide. And we're going to consider again these three statements. So one is that this columns of matrix, which now might be quaternionic, that they yield a cubature formula for HOM FDTT over the unit sphere. The second statement is that the outer products of the order T tensors give us something that is a tight frame for the symmetric tensors. And the third statement is that if we sum up the 2 powers of the absolute value of all the inner products, then we get some constant, where the constant's given by this formula, times the sum of the norm squareds, that sum squared. So like before, then if t is greater than 1 and we're dealing with the reals, then 2 can never hold. And this is also true for the quaternions. So 2 cannot hold, and it has to do with the fact that this constant CTDF is not equal to the dimension of the symmetric tensors. So that's only the case when we're over the complexes. And also we have this bound that when t is equal to 2, because remember we're focusing on 2 designs, and d is strictly greater than 1, then the size n has this bound that involves this m and the dimension. And if you plug things in, then you see for the complex case, this just says that n is less than or equal to d squared, which is precisely what we saw already. Okay, so complex projective 2 designs and cousins. So I said I'm talking about quaternions, but let's keep thinking about complex for a second. So what does this 2 say? This very, very special statement that doesn't seem to hold for the reals or the quaternions, at least when t is greater than 1. So what it says is that the outer products of these symmetric tensors give us a tight frame for the space of symmetric tensors. So specifically, it says that projective 2 designs over the complexes yield tight frames over the d+1 choose 2, which is equal to this constant over 1 dimensional space of the symmetric 2 tensors. So further, an equiangular complex projective 2 design, i.e. a SIC, that means that it yields an equiangular tight frame for SEM2 CD. So we always get that it's a tight frame if we start with a projective 2 design. But if our projective 2 design was also equiangular, then when we play this game with the outer products of the tensors, we actually get an equiangular tight frame. So one might want to call this a cousin ETF. So it's somehow arising from this first ETF. And ETFs with these particular parameters are plentiful. The sort of cousin ETF size. So I should say that this G3, the set of 9 vectors, is both a SIC, and I guess it has the parameters of a Naimark complement of a cousin ETF. I don't want to say Naimark complement, but if that means something to you. And there's a generalization of this construction for other prime powers that also give parameters of cousin ETFs. So, you know, there's maybe some hope that if you study the cousins, it gives you information about the existence of some SICs. But I've already stated that over the quaternions, 2 cannot hold. So can we get something cousin-like that if we have a projective 2 design of the quaternions, we get something? And the answer is yes. So we note first, if we look at that constant that we are getting and we look at the reciprocal of it for t is equal to 2, then what we get is d times 2d plus 1 divided by 3. So that's not the dimension of the symmetric tensors. So we know the symmetric tensors of quaternionic projective 2 designs, it can't form a tight frame for the symmetric tensors. However, if you take any vector, non-zero vector, in d-dimensional quaternionic space, you can very easily generate a 3-dimensional real space of the anti-Hermitian operators in d by d quaternion matrices. So this sounds really complicated. This is a fairly common trick to think of like quaternions in the term of like 3D rotations. So the idea is we take this vector and we map it to this space where we take the vector x and we map it to x times z times x transpose, where z is a scalar h, but remember we're in the quaternions, so order matters. Z is a scalar in h such that the real part of z is 0, so it's an imaginary quaternion. And this is a 3-dimensional space, real 3-dimensional space, inside the space of anti-Hermitians. And hey, the anti-Hermitians, they have as real vector space dimension d times 2d plus 1. And hey, I remember that. That was the numerator of the reciprocal of that constant. But we had this 3 hanging out on the denominator. That's a little weird. Oh, but wait, our subspaces are dimension 3. So it's very suggestive, but it ends up actually being true that if you play this game and the x that you put in to this U are precisely the elements of a quaternion projective 2 design, then what gets spit out is a cousin tight fusion frame of three-dimensional subspaces. So you can think something that's like a tight frame, but instead you're lobbing together subspaces. And in particular, if you started with an equiangular quaternion projective 2 design and you play this game, then what pops out is a cousin equi-isoclinic tight fusion frame, or equi-isoclinic is a very strong generalization of equiangular, but with subspaces. Okay, running short on time, so let's get to this result 3. It says one can, if you're very careful, define projective 2 designs over finite fields. And a construction of an infinite class of such designs generalizes the construction of this set of 9 vectors in three-dimensional space. Okay, why finite fields? First of all, it's fun. Certainly more fun than the octonions, which we banged our head against the wall for a while trying to figure out this summer. Second of all, the existence of complex ETFs, including SICs, implies the existence of ETFs over infinitely many finite fields. So this is another thing where, hey, maybe if we study these sort of cousin-y objects in the finite field case, it gives us information about the SICs. Also, the existence of certain ETFs over finite fields implies the existence of certain real ETFs, so possibly new classes of strongly regular graphs. These results here, there are 2 different papers that have used different sorts of inner products for finite field frames by Gary and Joey and John and Dustin. So if this is really interesting to you, you can check it out. And finally, why finite fields? You can see the introductions to the papers for further rationalization, I mean motivation of why one would actually want to do frame theory over finite fields. Okay, so what's the deal with inner products? We need to define an inner product to have any idea of what frames are. So let's just let F be any field. So right now that could be real or complex as well. And sigma be any field automorphism such that sigma squares is the identity. So for example, we could consider the complexes and sigma is complex conjugation, the reals and sigma is the identity, or in this case, a finite field over Q squared elements where Q is a prime power, and then our sigma just maps alpha to the Q. And so let's define for any vector in d-dimensional space over this field F, X star is, well, we kind of think but what we do in the complexes. And so we apply the sigma to every coordinate and we do the transpose. And so we can just define an inner product on FD that just maps X comma Y to X star Y. Look at us being like physicists here, complex, linear in the second. But I'll note here that this inner product will in general not be positive definite. So I'm calling it an inner product, but if you define an inner product as being positive definite, that's not going to happen. So as a very simple example, let's just take the vector 1, 1, 1 as viewed as a vector in three-dimensional vector space over F3. Then X is clearly not the 0 vector, but if you take the inner product of itself, you get 3, which is just 0. So you have a lot more zeros popping up that you might be thinking about when you're thinking about characteristic 0 fields. So in particular, you have to kind of define a certain kind of subspace that's like acts like characteristic 0 in a sense, and it's called non-degenerate. And so let V be some subspace, vector subspace of FD. Then if V and V perp are intersect, and that shouldn't be the empty set, that should be 0. Next little typo. I'm going to fix all these typos and I'll upload the slides to the website. So V perp is just like a normal linear algebra. It's just all the vectors in FD. So it's the inner product of F with all the elements of V is 0. And so just like you can have a vector with itself have an inner product equal to 0, then you can have other weird things happening. So we're trying to restrict ourselves to subspaces that aren't so ugly. Okay, so one more time, let's go back to this what's the T, and let's recall what we did over these statements we had over the reals, complexes, or quaternions. So we had the three statements. One was the VJ give us a Cubature rule. The other was that the outer products of the tensors, order T tensors, give us a type frame for those order T symmetric tensors. And finally was if we sum up the 2t powers, the absolute values of these inner products, then we get some constant times the square of the sum of the norm squares of the vectors. Okay, so keep that in the back of your mind. So a little bit of frame theory over finite fields. And I want to make a comment here. This is not quite coding theory because you're really basing this on inner products and not Hamming distance. So I used to just say frame theory is coding theory, characteristic 0, but this is showing that what I've been saying for years is wrong. Okay, so let's let V be a non-degenerate subspace of FQ squared. And we let phi be this set of phi j. So what we're going to do is we're going to channel this 2 thing, which is that the outer tensors give us a type frame for the symmetric. Outer products of the tensors give it a type frame for the symmetric, or in this case, we're just T and 2, so we want the outer products of the vectors themselves to sum up to some constant multiple of the identity. So we define phi to be a C-type frame if the vectors span the space and we have the sum of their outer products is equal to C times the identity. So, you know, normal frame theory, you don't also need to say the span is the entire space, but you do in this case. And we call a C-type frame an ABC ETF. If you take the inner product of any vector with itself, you get A, and the inner product of any 2 vectors, you get B, 2 distinct vectors. Okay, so let's get to the projective T designs. So we let Q be an odd prime power, and we are there's another typo. That's not FQ2. We're looking over D-dimensional space over the field with Q squared elements. So we're channeling this 2 again, and that should be a lowercase t. So we're kind of piecing together that we have a 1 design and a 2 design. So we call phi an A, C1, C2 projective 2 design if the inner product of phi j with itself is A for all j. If phi is a C1 type frame for again, this is the wrong space, but the D-dimensional space over the field with Q squared elements. And finally, that the 2 tensors of the phi j's is a C2 type frame for the important, this is actually a non-degenerate subspace of the symmetric tensors. Note that the C1 or C2 could be 0. So there's some cases that have to be handled here. And I also want to say that this, we're using this cubature a lot, but it's actually kind of junk over the finite fields because when you're integrating these homogeneous polynomials, you're just getting 0. So that's not something that we want. So the question is, are there small enough projective 2 designs that are equiangular, just like in fields of characteristic 0? And the answer is yes. And because I'm running short on time, I'm just going to fly through these, but like I said, I'll upload the slides. So the first thing, and I guess I won't fly through this slide, this is one of the main results of the paper, that if we have Q is an odd prime power, and we have a set of vectors in the D-dimensional space over the field with Q squared elements, then any 2 of the following statements apply. The third, 1, phi is a projective 2 design. 2, n is equal to d squared, so this number of vectors. And 3, there exists an A, B, C1 in the field FQ, so Q elements, not Q squared, such that, well, there has to be some constraints that are case-based on the parameters, and also phi is an A, B, C1 equiangular type frame. So any 2 apply the other, which is very similar to what we see in, for example, the complexes. What about the promised construction? Well, I guess I lied to you because there's no time for that, but it uses some cool combinatoric stuff with different sets. And it's something where it's basically a construction that if you play it over the complexes with few exceptions, like here, this G3 is one of the exceptions, but in general, if you play this game over the complexes, you don't get something equiangular, it's biangular. But If you play it the right way over the finite fields, then you get something that is actually equiangular. And again, there's running short on time, so I just want to finish up. A ton of further questions. First of all, for all the experts out there, have we missed something big, well known? Like a lot of this stuff was really new to us, so it's possible that there's some big thing that we weren't aware of. Another further question is it possible to relate the entanglement breaking rank of channels, which are just perturbations of that quantum depolarizing channel, to weighted complex projective T designs? That might actually give us a little more leeway to like chip away at this weak Zauner. Another question, are there cousins of real projective T designs? So by playing the sort of staring at what this constant is, when you sum up all of the fourth powers of the inner products of the vectors, you would expect that if there is some sort of cousin object, it's somehow three-dimensional subspaces of some real D times D plus two-dimensional space. It's not clear if they exist. It's, yeah, we looked at it for a while. Maybe you can prove they can exist. Maybe they're there. Maybe we're doing the wrong thing. I don't know. Is it easier to disprove the existence of certain real equi-isoclinic packings in order to disprove the existence of equiangular quaternion projective T designs? And so I rephrase this as, is H Zauner or Gillespie? So, over Zauner, there's conjecture that you always have these equiangular complex projective T designs, but Gillespie's conjecture says that there's only a finite number of equiangular real projective T designs. So we're leaning towards quaternions being like Gillespie and only having finite number of such things, but it's not super strong because we don't have a whole lot of experience with the quaternions yet. Also, one can define octonian projective T designs when you're in 2- and 3-dimensional space. Does any of the stuff we do generalize? With just a huge warning, really only if you are like a huge masochist get into this, but maybe you're like hate yourself more, or just are more talented and can figure out some things with octonians. And then finally, there's this mapping where we're taking vectors and we're mapping them in quaternion vectors into 3-dimensional subspaces. Does that yield particularly nice subspace configurations when applied to maximal MUBs, aka Kurdot codes, like in Bill Cantor's paper from '95 that constructed these things? So thanks for your attention. I look forward to the discussion. And thanks to Steve for reminding us that we should now always be saying, don't forget to like, rate, and subscribe. And then there is my website. So yeah, thanks.
All right. Thanks, Emily. I'm going to encourage everyone to hit that reaction button. Sorry, smash that reaction button. Did we ended the recording?